Hi everyone, Ferris here with a few words about symmetry. If your experience was similar to mine, perhaps you first encountered the concept of symmetry in the visual arts. The bilateral symmetry of the human body, the mirror symmetries of structures like the Taj Mahal, the translational symmetries of M.C. Escher, and the frieze of the Parthenon, and the many internal symmetries found in the music, for instance, of Johann Sebastian Bach, which is why we put Bach on the Voyager Golden Record, or the rotational symmetry of a sphere like our old friend the lacrosse ball here, which is symmetrical in that it can be moved around. You can look at it from any angle and it always has the same symmetrical shape. In science, however, symmetry is defined as having a property which remains invariant, that is to say unchanging, through a transformation, such as rotating a ball or moving an object around in space. The point I'd like to make in this talk is that all scientific statements about laws of nature, and scientific theories more generally, are statements of symmetries. They are theories that identify something in a system that remains unchanged throughout a transformation. The laws of thermodynamics, for instance, were adduced back when steam engines were being perfected, and they made it possible to trace a quantity, energy, that remained unchanged throughout the workings of a steam engine. You could trace how much of the energy got lost through friction and noise and such, and how much of it wound up being done as work, which can be defined scientifically as the scalar product of the vectors of force and displacement. So symmetry is fundamental to the scientific view of the universe. But perfect symmetry is sterile. Let me take as an example a classic symmetrical object, the form of crystallized carbon called diamonds. Now, I don't happen to own a diamond, but I do have some carbon here in this pencil point. And the only difference between this carbon and the carbon in a diamond is that to make a diamond you have to compress the carbon to the point that all the carbon atoms lock down into a minimum energy configuration. And all a diamond is just a repetition of that configuration over and over again. The reason that the atoms seek that configuration, by the way, is that it is the lowest energy point they can find. And nature will always move to the lowest energy alternative that's available to it. Now, this is actually material that came off the brake discs of a Formula One car. And you can see there's some crystallization in there from the heat that up to 1,000 degrees Fahrenheit that those brake discs undergo. So this is another form of carbon crystal of which the aesthetic ultimate is the perfect diamond. Back when the De Beers Corporation was marketing diamonds under the slogan, "A diamond is forever," people became aware of really the great selling point of diamonds, as with gold, that they don't change. In fact, the word diamond comes from the Greek for unchanging. But that's just the problem with diamonds. Because they're unchanging, you can't really do much with them except admire them, and they're used for some industrial purposes, of course. But they're not creative. Perfection is sterile. All a diamond can do is just keep on being a diamond. So in short, perfect symmetry, though much discussed, is sterile. But if the universe is symmetrical at its root, as revealed by the symmetries found in the so-called laws of nature, and if symmetry is sterile, then how come the universe is not sterile? How come biological creatures like us can exist? And the reason is that some of those underlying symmetries were broken in the early Big Bang evolution of the universe. The example that scientists like to use is the magnet. Here's an ordinary bar magnet, has a north and south pole. If you heat it up enough to what's called the Fermi temperature, it will lose its magnetic properties. Let it cool off again and it will reassume its magnetic properties. The magnetic field will return. But the question of which end is north and which is south will be arbitrary. Half the time it'll be the same orientation that it was before, half the time be the opposite. In fact, magnetic objects do this by themselves quite often. The Earth, for instance, has reversed its magnetic pole many times. The Sun reverses its magnetic polarity about every 11 years. The fact that many of the symmetries in our universe are broken is so important to physicists that Robert Wilson, the sculptor and physicist who used to run the big Fermi accelerator in Illinois, created a sculpture called Broken Symmetry, which stands at the entrance to the lab. Biological evolution gives us an example of broken symmetry. If the RNA-DNA transfer of information from generation to generation were perfectly symmetrical, in other words, the information simply repeated exactly the same through every generation of each species, then there would be no evolution. All life on Earth would still be stuck at something like the level of the first cells. But the RNA-DNA information transfer is not always accurate. There are internal errors, things like cosmic rays can damage the code, and it's those mutations that create innovation that make evolution possible. So broken symmetries are the reason that there's so many wonderful species of life here on Earth and quite possibly on other planets too. On the cosmological level, gravitation, which appears to be a unipolar force, not much is understood about gravitation at the fundamental level yet, but we look around us, gravitation is always attractive. It doesn't have another pole the way magnetism does. That broken symmetry meant that the Big Bang, instead of just dissipating as a gas forever, instead was able to create structures that the gravitation pulled together material to form stars and planets and galaxies, and to make possible the many innovations we see in the universe today. So to sum up, there is such a thing as symmetry. There is a concept of perfect symmetry, which is part of the broader concept of perfection. But the universe we live in is not perfect thanks to broken symmetries that make it possible to have all the diversity and creativity of the universe as we experience it. So for all you creative artists out there, if you're writing books or poems, singing songs, making paintings or videos or whatever, don't try for perfection. It doesn't exist. There's no perfect sphere in the universe. There's no straight line. The real world is asymmetrical and imperfect, and your work can be too. There's no point in trying to make it perfect. Just make it as good as you possibly can. That'll be quite good enough. And certainly, don't look for perfection in human beings. There's no perfect master who can teach you the right way to live. There's no perfect person that you have to find or else you can never get married. They don't exist. Or as Chrissy Hine put it, nobody's perfect, not even a perfect stranger. Hey, thanks for listening. See you next time. Recommended reading for this lecture, Ian Stewart, Symmetry, in the Oxford University Press Very Short Introductions series, and Scott Muller, Asymmetry, the Foundation of Information. Scott's thesis is that symmetry denotes no information and that all information in the universe arises from cosmic asymmetries.